Alright, so now we're moving on to Leetcode problem number 3243, that is shortest distance after road addition queries 1. So basically this is a medium level problem marked on Leetcode. We're given an integer n and 2D integer array queries. There are n cities numbered from 0 to n minus 1, and initially there is a unidirectional road from city I to city I plus 1 for all I belonging to 0 to n minus 1. 0 is inclusive and n minus 1 exclusive. So queries of I is equal to ui comma vi, which represents the addition of a new unidirectional road from city ui to vi. So there's a directed edge from u to v, right? So there's a directed edge from u to v. After each query, you need to find the length of the shortest path from city 0 to city n minus 1. So we see that we have to find the shortest path, so that is clearly indicative of Dijkstra's algorithm that will be used, right? And since we are dealing with you can see that there's a unidirectional road and there are no weights given to us, so basically we can also use BFS here. So I'll share, firstly let's go over the examples, then I'll share the how you can approach this problem in two different methods. So we need to return an answer array answer where for each I in the range 0 to queries of length minus 1, answer phi is the length of the shortest path from 0 to city n minus 1 after processing the queries, that is the first I plus 1 queries. Okay, so let us say this is the queries, right? So basically this means there's a node being added from u to v in each of these queries. So this was the graph given to us. How did we form that graph? So basically it's given to us in the problem that there's a node from I to I plus 1, node from I to I plus 1. So the values of I fall in the range 0 to n minus 1, and n minus 1 is excluding it, right? So if n is given to us as 5, so I would be belonging to 0 inclusive and 4, that is n minus 1 exclusive. So basically we have 0, 1, 2, 3 and 4. Sorry, not 4. I would be 0, 1, 2, 3. I plus 1 would be so I plus 1 would be 4, right? So 0, 1, 2, 3 is the I values. So we form a graph. So that would be 0 to 1, since it is I to I plus 1, 0 to 1, then 2, then 3, and then I to I plus 1. So basically I value if we have as 3, that is the final value, then we have I plus 1 as 4. So this is the graph that is formed, and this is the exact same graph. So let me erase this first, right? So now the queries vector of int type is given to us, that is u to v. So basically 0, 1, 2, 3, 4, you can see that there's a node that is being additional node, which is a unidirectional node, that is a directed edge going to be added from 2 to 4. So from 2 to 4 we added this edge, right? So now we basically need to find the shortest path firstly and store it in this, right? So in the answer vector we'll be storing our shortest path from the starting node and the end to the end node. So from 0 to 4, you see from 0 to 1 we have 1 distance, then we have 2 distance, and we can directly reach here, so we have 3 distance. So that is why we store 3 here. Similarly from 0 to 2, if we add another edge, so that is this edge being added, so this is distance 1 and this is distance 2, that is decreased our shortest path from 0 to 4 to 2, right? And finally we have 0 to 4. A direct edge from 0 to 4 would mean that we would only have to require a single step to reach here. So after the addition of road from 0 to 4, the length of the shortest path from 0 to 4 is 1, and that is why we store it here. So you basically got the gist of this problem, and now let me share this example, another one. So n is equal to 4, so we have this as the graph that is formed, and queries is equal to 0 to 3. So from 0 to 3 we have the queries, and then we have 0 to 2. So we need to find the shortest path, right? The length of the shortest path in this case would be 1, and even if we add another edge, we see that this path would be taking two basically shortest 2 edges to reach from 0 to 3, but we already have a shortest path which is shorter than the length that has been added, so that basically makes it 1, and that won't be updated, so we have only 1, right? So that is the answer. So now let us get to our solution. So basically I told you about the Dijkstra that we can apply, and also by BFS, since we are dealing with weights, right? So initially the graph is a linear chain 0 to n minus 1 with each edge weight as 1. So we receive multiple queries, each adding a new directed edge u to v with weight is equal to 1. Now after each query we need to return the shortest path length from 0 to n minus 1, right? So our first approach is basically the Dijkstra's algorithm, in which we use a priority queue as our data structure, right? So the key idea is that since the graph is weighted, that is the weight is equal to 1 for each of these edges, right? So we can use Dijkstra's algorithm here to recompute the shortest distance after each query. The complexity per query would be O of E log V, where E increases as the queries add edges. E is basically the number of edges, V is the number of vertices. And the total complexity would be O of Q times E log V, because we are going over each of the queries. That is, the Q is the length of the queries vector that we have, right? so the one that you saw in the previous example. Now the algorithm sum is going to be like this, that we initialize the graph with edges first, that is I to I plus 1 with weights equal to 1 for I is equal to 0 to n minus 2, because the range, as I told you, I is 0 to n minus 1 excluding that, so 0 to n minus 2 including it. So this is the i's range, so that is here I mentioned. Now for each query, u comma v, add a direct edge u to v with weight 1, run the extra from 0 to n minus 1 and store the shortest distance result. And the complexity we have discussed, right? Now this is the solution for the Dijkstra's algorithm. So I've set the alias name of a pair of int comma int to p, so that it becomes more readable and faster for us. So this will be storing our weight and node, so that is why pair of int comma int. Now we declare our adjacency list globally, that is a node map of int comma vector of pair of int comma int, that is u, it will be storing something like u and v comma weight, right? So this is the format, and weight is equal to 1, right? So for each node from u to v and with an edge weight of weight, so this is u to v and the edge weight is weight. This is the edge that is being added here. For each of those edges, we'll be adding it to our adjacency list. Now Dijkstra's algorithm, we call it, firstly let me show you shortest distance. This is the function that we have after queries. Queries is passed and n is also being passed as parameter, which is the number of edges, right? So for I 0 to basically I is going from 0 to n minus 2 and including these values, so that is why we take it up to n minus 1 less than not equal to, right? So we form a graph adjacency of I dot push by I plus 1 and 1, so treating each edge weight as 1. This is weight, so we have added the weight as well as the node that we are going to, that is v, and this is u and this is the weight. Now q is queries dot size vector int res is our result. So for each query we traverse it, this would basically u is equal to q of 0, and basically in q we were storing u and v, that is from node u to v. So that is why we push into the adjacency list of u, v and 1, that is the edge weight is equal to 1, and we call get the d value, that is the shortest distance from Dijkstra of n, and we push it back into our result. So that is why we recompute the shortest path and we return it. Now this basically Dijkstra is being called. This takes a single Dijkstra would be taking O of e log v, but since we are in a for loop which is running for q times, that is for size of queries, right? So q is also multiplied here, and that is why we have this time plus complexity. Now moving on to our main function, that is our Dijkstra's algorithm. So it takes the n, and that is the number of nodes for that graph, right, as our parameter. So we store vector of int res, and we have initialized it with int max. Res of I would be storing our shortest distance from source to the ith node, and we mark 0 res of 0 as 0 since we are starting from the node 0. And we also take a priority queue of this type with greater of p as our comparator. That means we are storing it in the form of a minimum heap, and we store distance and node since we are taking pair of int comma int. Now pq.push 0, 0, basically starting from node 0 with a distance of 0. While the priority queue is not empty, we extract the current or the topmost element and store it in current and pop it out from the priority queue, and we get the distance as current first and node as current second, and we check if node is equal to n minus 1. If the node that we are at is the final node, that is the destination node that we had to reach to, we return the shortest distance required to reach from node 0 to n minus 1, that will be stored in res of n minus 1, right? Res of n minus 1 is shortest distance from source to the n minus 1th node, that is our destination node, and that is what we require. So we terminate here. In case this is if node is not equal to n minus 1, that is we have not reached here, so we continue to the next condition, that is for each neighbor and weight in the adjacency of node, if distance plus weight, a standard Dijkstra. So we check if the distance, current distance plus the weight of the node, that is equal to 1, right, is less than the value stored in our result vector, right, then we update it because this is a smaller value. So we update res of ne as the same value, distance plus weight, and we push the distance plus weight plus the neighbor along with that, since we are storing the distance as well as the node. So the updated distance and the new node, that is the neighbor, and we perform this for loop, and basically this will run till the priority queue is not empty. In case it comes out, we return -1. Otherwise, in most conditions, it would be basically reaching the destination node, and we'll finally output our shortest distance to reach node n minus 1, that is our destination node, from 0.